Hello and welcome to Concept Booster Tutorial or CBtutorial.com. Through this, we give online, offline courses to the students of class 10 and 12 pursuing winter crash course for the upcoming board 2020-2021. This is a trial class for the class 12 physics student. In the last class, we discussed about electric dipole. We also discussed the net charge of an electric dipole. We also discussed electric field produced by electric dipole on its axis, on its axial line. Today, taking the discussion little further, we will discuss about the electric field the electric dipole produces on its equatorial region, these regions. Yesterday we discussed only about, in the last class we discussed only about the points lying along electric field on the points lying along this line. Today we will discuss about the electric field produced in this region, here, in these regions. And also we will see whether the electric field produced by the electric dipole be larger or smaller than the one produced in the axial line. We will also see what will be the direction of electric field in this case, and we will compare it with the case we discussed in the last class. As we already discussed this in details in the last class, that a dipole is a system of two equal and opposite charges. We also discussed that a dipole is a vector. It is a vector and its direction is always from negative charge to positive charge. This is the direction of the electric dipole. Today, what we will do is that we will calculate the electric field produced by this electric dipole on equatorial region. For that, let us take a point P. Let us take a point P at a distance r from the center of the dipole. So this is the center of the dipole, and at a distance r from the center of the dipole we take a point P. Let this be a point P. Let this be a point P at a distance r from the center of the dipole. You might be knowing from the last class that the net electric field produced by the electric dipole at this point will be given by the vector sum of the electric field produced by each charge at this point. So for this charge, positive charge, this should be the distance between the point where the charge is located, where the source charge is located, and the point where we are interested to calculate the electric field. However, as I discussed in the last class also, electric field is a vector. Electric field is a vector. So whenever we are discussing or talking about a vector quantity, you must have complete knowledge about the direction in which it is acting. So since this is a positive charge, we discussed in the last class also, and you might also be already knowing that the direction of electric field due to a positive charge is always radially outward. So the direction of electric field due to the positive charge will be in this direction. So this will give the electric field at this point P due to the positive charge E plus Q. Similarly, for this point, for this charge, for the negative charge, this should be the distance, this should be the distance, okay. And since we are talking about electric field, we should specify its direction also. Since the source charge is negative, the direction of electric field will be radially inward. So direction of electric field for this case will be radially outward, that is in this direction. In this direction. This will be the electric field due to negative charge. One thing you should know here, let us talk about the magnitude only. Let us not talk about its direction, magnitude only. Will the magnitude of electric field produced by this charge and the magnitude of electric field produced by this charge be equal? Will numerically equal? This is a question. For that, as you all know that electric field is given by E is equal to K Q by R square. We are talking about magnitude only, so let us not take its direction. Let us not be concerned about its direction. If this Q and R are same, if the charge and the distance are same, then their two electric field will be numerically equal. Let us say in this case, for both this E plus Q and E minus Q, the source charges are same. Since it is a dipole, two equal or opposite charges, so two charges are equal in magnitude, so this is valid. What about the direction? Direction are also not direction, distance. The distances are also same in the both cases. Why? Because this point is taken from it is perpendicularly above the center of the dipole. So from center of the dipole, for the both charges, this distance will be same. So since charges are also same and the distances are also same, then these two electric field magnitude of these two electric field are equal. This also we can say about this. Okay, the magnitude of both are equal. Now, this is the direction of electric dipole. Now let us specify the net direction of the electric field here. Before going into that, let me explain you one simple rule of vector. Those who are not from mathematics background might not be knowing this, that a vector can be resolved into two components. Let us say if this is a vector, let us say a vector A. Okay. Then if it is a vector, then this vector can be resolved into two components. One component we call horizontal component, which is in this case A cos theta. If this angle is theta, okay, if this angle is theta, then the horizontal component of a vector will be A cos theta, and the another one is a vertical component, okay, and the vertical component will be A sin theta. Okay, you should know that this wherever this theta is taken, that component is taken as A cos theta. Okay, so any vector can be resolved into two components. One is horizontal component, another one is vertical component. So having known this, now this case will become very easy. Now let us talk about this. Let us talk about this. E plus Q. Like in that case, it will also have two components. So those two components will be, one will be this. Okay, one will be this, which is if this angle is theta, okay, E plus Q cos theta. This is our horizontal component. Similarly, it will have a vertical component also, which in this case will be E plus Q sin theta. Okay, so this will be the horizontal component and vertical component for E plus Q. Similarly, for E minus Q, since it is also a vector, it will also have two components. So one component for this will be, again, this will also be a theta. Again, this will be its horizontal component, which will be E minus Q cos theta. And for this, it will be the vertical component, which will be I am writing this here, E minus Q sin theta. Now look at this, E plus Q sin theta and E minus Q sin theta. Let us look at this two components. E plus Q and E minus Q are numerically same. Sin theta, since theta are same, so both sin theta will also be same. That means these two components are equal and their directions are opposite to each other. As you can see, this is pointing upwards and this is pointing downwards. Both are the magnitudes of both components are same. Therefore, the two vertical components are cancelled. Okay, so in this case, no vertical component will remain. So what will only remain is horizontal component. What will only remain is horizontal component. So the net electric field, let us call it E. Net electric field E will be E plus Q cos theta plus E minus Q cos theta. Only the horizontal component remaining. Horizontal components remain, the vertical components are cancelled out. Now let us discuss about its direction of the net electric field. It is clear from the picture, the direction of the electric field will be in this direction. Since we don't have these directions, so this will be the direction of net electric field. That means, what is the direction of P? The direction of P, electric dipole moment, is from negative to positive. So this gives the direction of electric dipole moment. Then the net electric field will be in the direction opposite to dipole moment. So if we use vector, if we use a vector here, then it will be in the direction of minus P cap. So direction of net electric field will be minus P cap. So if you simplify this little further, little more, this minus will come out here, and E plus Q plus E minus Q cos theta, a common cos theta P cap. Okay, so this will be the net electric field due to electric dipole on equatorial region. Now it is very simple. It is now very simple. You can calculate E plus Q, you can calculate E minus Q, you can calculate cos theta. So if this is theta, then this will also be a theta. Okay. Now the case has become very easy. Now what will be E plus Q? Electric field due to this will be K Q by this direction, about this distance. Here we apply Pythagoras theorem. So using Pythagoras theorem, you can see this is a triangle. So in a triangle, this is the longest side of the triangle, which is called hypotenuse. So hypotenuse square is the distance. Okay, so we are concerned with this distance. Okay, so hypotenuse square of this distance, which means hypotenuse square. So which is given by, if this is the R, let us call it R1 square. Okay, so R1 square will be A square, this distance is A, plus R square. So this distance will be A square plus R square. Similarly, magnitude of, let us take already its magnitude. Okay, यो जुन चाहिँ मोडुलस को साइन छ, मोड को साइन छ, यसले म्याग्निट्युड मा भएको बुझाउँछ. So E minus Q कति हुन्छ? Similarly, E minus Q हुन्छ K Q by again A square plus R square. We are taking only the magnitude. Now cos theta, cos theta कति हुन्छ? So cos theta you can take for this theta. Okay, so cos theta भनेको कति हो? Cosine of theta base by hypotenuse. So for this triangle or for this triangle, both are same. So for this triangle, cos of theta will be base is a, this distance is a, and hypotenuse is this distance. Again, hypotenuse is this distance, then let us call it R2. Then R2 square will be a square plus r square. But we are not, we need not square r2 square, but we need R2. So which will be under root of a square plus r square. We can write this as a square plus r square to the power half. Alright, so this will be divided by a square plus r square to the power half. Now we apply the value of e plus q, e minus q and cos theta in this equation. Let us call it equation 1. Okay, so if you apply the value of all these in equation 1, what you will get is the net electric field due to electric dipole on its equatorial region. Okay, I am doing it here. E will be minus E minus Q is KQ by A square plus R square plus KQ by A square plus R square. We have cos theta also. Cos theta means A by A square plus R square to the power half. Direction is p cap. Minus, you can see here, now both these two are same, they are like term, so you can directly add them. 2kq by A square plus R square, A by A square plus R square to the power half p cap. Then now look at this, you have to multiply these two, so this will be 2kqa, and in this case, as you can see here, bases are same, A square plus R square, here also A square plus R square, and their exponent or powers are, here we have 1 as the power, and here we have 1 by 2 as the power of the base. So we can, since the bases are same, power are added. Simple rule of mathematics. This will be A square plus R square to the power s to power 1 plus s to power half. Direction again p cap minus p cap minus. Now you know the value of k, it is 1 by 4 pi epsilon naught. Again 2 and QA, मतलब Q into 2A हो, this means Q into 2A. Q into 2A भनेको हामीलाई थाहा नै छ, Q into 2A भनेको के हो? Q into 2A भनेको हो dipole moment. So you can write this as P. You can write this as P. You can write this as P by, now what we have here? A square plus R square to the power 3 by 2. 1 plus half is 3 by 2. Now, since we are using P directly here, dipole moment directly here, which is a vector, so the direction of this itself will be the direction of electric field. So no need to put a different unit vector here. Okay, if you are already using a vector, then no need to use unit vector. But in this case, we are not using any vector here. That is why, in order to show the direction of this term, we are using unit vector. The function of unit vector is to show the direction. But in this case, we are using a vector here, so no need to use unit vector. Okay. So again, for r is far greater than a, like in the previous case, this will be 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught p by r cube. So this will be the net electric field due to electric dipole on its equatorial region. Okay, let us compare this with the cases we did in the last class, that is for the axial case. You know, for axial case, electric field, what was the electric field for axial case? 1 by 4 pi epsilon naught 2p by r cube. Okay, the sign was plus. That means in axial case, the direction of electric field was in the direction of dipole moment. Okay, because there was no minus there, it was a plus p. No, so that means for axial case, the direction of electric field is the same as the direction of electric dipole moment. However, for equatorial, the direction of electric field is opposite to the direction of dipole moment. So that is why we have minus here. So minus, the significance of minus is that the direction of electric field is opposite to dipole moment. First thing. Second thing is, if you look at the magnitude only, if you compare the magnitude only in the case of axial and in this case, you will find that in axial case, the strength of electric field was double as compared to this case, because in the axial case we had twice p. Okay, so that means in axial case, the electric field strength of axial is double the electric field of dipole on its axial region. On this note, I conclude this lecture here. Thank you.